Lights are red and there's sweat on your embrace. Just one other thing I dare. Lights are red and there's time to your embrace. Just another dare. Lights are red and there's sweat on your embrace. Just one other thing I dare. Lights are red and there's time to your embrace.
Restrictions and domain. To obtain the restrictions, first we have to simplify the function in both sides, and we obtain x minus 2 times x minus 1 over x minus 1 times x plus 1, and then we obtain x minus 2 over x plus 1. The term which eliminates something of the numerator is the gap, so we equals to 0 and isolate x, and we obtain x equals 1, so that is the gap, and the other term is the asymptote. We equals to 0 and then isolate x, so is equal x equals minus 1, and that's the asymptote. And with this information we can know that x belongs to all the real numbers except minus 1 and 1. So that's the domain. X and y intercept coordinates. First, to obtain the y-intercept, we have to evaluate the 0 in the x. So we get minus 2 over 1, and this is equals to minus 2. So the y-intercept is 0, minus 2. To obtain the x-intercept, we have to equals to all the function to 0, and we pass the x squared minus 2 to the other side, multiplying 0, and we get x squared minus 3x plus 2. This is a perfect square trinomial, and we get x minus 2 and x minus 1. We isolate x, and the x-intercept will be 2, 0 and 1, 0. Symmetry with procedure. To obtain the symmetry, first we have to make the x negative. This is the original function, and this is the function with the x negative. The result of this is different to the original equation, so this is not even. To know if the function is odd, we have to make negative all the function, so we have to change all the signs, in this case of the numerator, and this is the result. So we can see that this is different to the original one, so this is not even, and not odd and not even, so this function doesn't have symmetry. Vertical asymptotes and gaps using all needed procedures. First, we have to calculate the limit of x when it approaches to minus 1 from the right. This is the original function, and we have to substitute the minus 1 in the x. We simplify, and we get 1 over 0 with the positive sign, and this is equals to positive infinite. And then we have to calculate the limit of x when it approaches to minus 1 from the left. Again, this is the original function. We substitute the minus 1 in the x, simplify, and we obtain 1 over 0 with the negative sign, and this is equals to negative infinite. So when it approaches to minus 1 from the right, it goes to infinite, and when it approaches to minus 1 from the left, it goes to minus infinite. Horizontal asymptotes using all needed procedures. First, we have to divide everything by the term with the biggest exponent. So we divide everything by x squared, and we get 1 minus 3 over infinite over 1. We eliminate this because this is 0, and we get 1 over 1, and this is equals 1. So horizontal asymptote is y equals 1.
The letter f indicates the first derivative of our function. To find the first derivative, we use the quotient rule. The quotient rule says that the numerator is multiplied by the derivative of the numerator minus the numerator multiplied by the derivative of the denominator, all over the denominator to the square. First derivative of our function is x squared minus 1 multiplied by 2x minus 3 minus the multiplication of x to the square minus 3x plus 2 times 2x, all divided by x squared minus 1 to the square. The first derivative is 2x cubic minus 3x to the square minus 2x plus 3 minus 2x cubic plus 6x to the square minus 4x, all divided by x squared minus 1 to the square. The final answer and the first derivative of our function is 3x squared minus 6x plus 3 divided by x to the square minus 1 to the square. The letter G is the I-test. That means that we need to find the critical points, the maximum and minimum points, the intervals where the function is increasing and decreasing. First, we need to find the critical point of the function. The first derivative of our function is 3x to the square minus 6x plus 3 divided by x to the square minus 1 to the square. First, we need to find the critical point. The critical point is found. We need to solve the first derivative over 0. So that means 0 is equal to the first derivative of our function. We need to clear the function over 0. X to the square minus 1 to the square is dividing, so we need to pass multiplying. So 0 times x to the square minus 1 to the square minus is equal to 3x to the square minus 6x plus 3. The result of 0 is 0 because any number multiplied by 0 is 0. So 0 is equal to 3x to the square minus 6x plus 3. We need to simplify the 3x to the square minus 6x plus 3. That is equals to 3x minus 3 multiplied by x minus 1. All this is equal to 0. So find the critical points. We need to clear the x's in the two terms. 3x minus 3 is equal to 0 and x minus 1 is equal to 0. Minus 3 is passed to plus 3 and minus 1 is passed to plus 1. 3x is equal to 3 and x is equal to 1. X is equal to 3 over 3 divided by 3 and x is equal to 1. So both x is equal to 1. So the critical point is x equals 1. We are going to determine the maximum and minimum points of the function from the derivative and the critical point that we got. The maximum point is if when x is equal to a and first derivative with the value of a is equal to 0, and change the symbol plus to minus. The minimum is if x is equal to a and the first derivative with the value of a is equal to 0, and change the symbol minus to plus. The critical point is 1, so we need to find the minimum point when x is minor than 1. For example, the 0. The first derivative with the value of 0 is 3 multiplied by 0 to the square minus 6 multiplied by 0 plus 3 divided by 0 to the square minus 1 and all this to the square. The result is 3 divided by minus 1 to the square, that is equals to 3 divided by 1, and that is equal to 3. So the first derivative with the value of 0 is major than 0. The second to the maximum is x is major than 1. So we need to comprovate by, for example, with the number 2. The first derivative with the value of 2 is equal to 3 multiplied by 2 to the square minus 6 multiplied by 2 plus 3 all divided by 2 to the square minus 1 and all this to the square. It's equal to 3 times 4 minus 12 plus 3 all divided by 4 minus 1 to the square. That is equals to 12 minus 12 plus 3 all divided by 3 to the square. That is equal to 3 divided by 9, and it's equal to 1/3. So that the answer is there is no minimum or maximum points in the graph of our first derivative. This is our graph of our function and the first derivative of our function, and that shows the intervals of decreasing and increasing, which indicates the second derivative of our function is the derivative of the first derivative. So our first derivative is 3x to the square minus 6x plus 3 all divided by x to the square minus 1 to the square. So we simplified our first derivative with 3x to the square minus 6x plus 3 multiplied by x to the square minus 1, all of this minus to the square. So our second derivative is a product rule. That means the derivative of our first term is multiplied by the derivative of our second term plus the second term multiplied by the derivative of our first term. So the second derivative is equal to 3x to the square minus 6x plus 3 multiplied by minus 2 x to the square minus 1 all by minus 3 minus 1 to the 3 to minus 3 plus x to the square minus 2 to the minus square times 6x minus 6. So the second derivative is equal to minus 6 to the square multiplied by x to the square minus 1, all of this minus cubic, plus 12x multiplied by x to the square minus 1 to minus cubic minus 6 multiplied by x to the square minus 1 to minus cubic plus 6x multiplied by x to the square minus 1, all of this to the negative square minus 6 multiplied by x to the square minus 1, all of this to the minus square. So our second derivative is equal to minus 6 to the square minus 12x minus 6 divided by x to the square minus 1 to cubic plus 6x minus 6 divided by x to the square minus 1 to the square. I indicates that we need to make the second derivative the concavity test. That means we need to find the inflection points and the intervals where the function has positive or negative concavity. First, we must find the inflection point of the function. So give f the second derivative of x is equal to 0, or the second derivative of x is no exist or no calculate. So the second derivative of our function is minus 6x to the square plus 12x minus 6 divided by x to the square minus 1 to cubic plus 6x minus 6 divided by x to the square minus 1 to the square. All of this to the square. So we need to simplify the value of x to a small number, for example 0. So the second derivative when x is equal to 0 is equal to minus 6 multiplied by 0 to the square plus 12 multiplied by 0 minus 6, or this divided by 0 to the square minus 1 and the result to the cubic, plus 6 multiplied by 0 minus 6 divided by 0 to the square minus 1 and the result to the square. So the result is minus 6 divided by minus 1 to cubic plus minus 6 divided by minus 1 to square. So that means minus 6 divided by 1, minus 6 divided by minus 1 plus minus 6 plus 1. That is equals to 6 plus minus 6. So the second derivative when x is equal to 0 is equal to 6 minus 6. So the result of the second derivative when x is equal to 0 is equal to 0. So when x is equal to 0 is an inflection point. Find intervals of concavity and the turning point in the graph. The graph is the graph of our second derivative of our function. So the graph shows the intervals when the concavity is downward and upward, and the point red is the inflection point. Graph the function and decide the range of the function. So we had the three graphs of the graphs of the function, the first derivative and the second derivative. Our function is with color green, the first derivative is with color red, and the second derivative is with color purple. And the range of our function is all the real numbers to the infinity to minus infinity.
I dare like to